Hello, everyone. Welcome back. So today I'm going to be talking about factorials. So this might seem a little bit out of place in this unit if you've ever done factorials before, because this unit is all about counting. But for a lot of counting techniques, we need to understand factorials and how they work if we're going to be able to answer those questions effectively. And so that's why these are very important. Okay. So let's talk about what does a factorial mean? Well, for example, if we have 6 factorial, that means 6 times 5 times 4 times 3 times 2 times 1. So it's basically starts with 6 and we multiply by every number till we get to 1. And it's the same pattern in general as well, right? If I have 4 factorial, that would be 4 times 3 times 2 times 1. If I have 10 factorial, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So in general, n factorial is equal to n times 1 less than n minus 1, times 2 less than n, which is n minus 2, etc. However many terms there are in the situation, all the way until it's going to end with 3 times 2 times 1. So let's calculate the following. Okay, so this one here asks us to tell us what 2 factorial is. So 2 factorial is 2 times 1, which is just 2. 4 factorial is 4 times 3 times 2 times 1, which is 24. And then 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Okay? So yeah, so that's basically that. Pretty simple, pretty straightforward. Now I will say that, these 3 questions here, these are far too simple to come up on a test unless, it'd have to be a really easy test for something like this to come up. So these are just examples to try to get us started, to get us understanding about factorials, but this will get harder. Okay, so now they're asking us to calculate the following here. Now we could do it just the same as we were doing up before, and we could say, well, 7 is 7 times 6 times 5 times 4 times 3 times 2 times 1, and find out what that is, and then find out what 4 times 3 times 2 times 1 is. Or we could actually cancel a bunch of numbers out. So I'll show you what I mean. We have for 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. And here we have 4 times 3 times 2 times 1, right? So 4 times 3 times 2 times 1, these can be canceled. And then all we have to do is find out what 7 times 6 times 5 is, right? And so that makes the question a whole lot simpler, which is fantastic. So therefore, it's going to be 210, and that just makes it a little bit easier on us than having to multiply out everything. I mean, if you have a calculator with a factorial button, maybe it doesn't make much of a difference, but when you're just doing it by hand, it's a lot easier just to multiply 3 things together. Good. All right, how about this example? Well, 10 factorial is equal to what? Well, that's going to be 10 times 9 times 8, and then times the rest of it, 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'm actually not going to write all those numbers out. I'm just going to say times 7 factorial in this case, because 7 factorial is the same thing as writing the numbers out. It's just shorthand. And then over 7 factorial. And I can just directly cancel out these 7 factorials and say, well, that means the answer is 10 times 9 times 8, right? Which means the answer is going to be 720 for that one. We can do the same thing here. In fact, we probably want to, because these numbers 50 and 51 are extremely large. So it would be very hard on us to actually, expand everything out fully. So for this one, I'm going to say this is 55 times 54 times 53 times 52 times 51 factorial over 51 factorial. These cancel out, and then we just have to multiply 4 numbers, which are 55 times 54 times 53 times 52, which is going to be about 8 million. Oh, wow. 8 million. 185. 320. That's a lot. Although we multiplied pretty big numbers together, and there were 4 of them, so it makes sense. Very good. All right. So next, let's calculate these here. Okay, so for these ones, I'm going to do them slightly differently. I'm going to say, well, what are our biggest factorials? And I'm going to go with those. So in this case, we have 7 times 6 times 5 times 4 factorial. and I'm going to cancel that out with a 4 factorial on the bottom, and I'm going to keep the 2 factorial as 2 times 1. So now I can cancel out these 4 factorials, and I just have 7 times 6 times 5 divide by 2, right? Is all I have left. So I still have to divide by something, but this way, because I took out the biggest factorial from top and bottom that we possibly could, I am leaving myself with a lot less work. All right, so let's do it out. 7 times 6 times 5 divided by 2 would give us 105, and so that's our answer. I'm going to do the same thing for B. I'm going to say, well, what's our biggest factorial for top and bottom? Well, for top, it would be 8. For bottom, it would be 4. So that means 4 factorial is what we'll be able to realistically cancel out here. There we go. So let's cancel those out. And then we have 2 times 3, which cancels out with 6. So we just have 8 times 7 times 5 on the top then. Oh, and I guess this 1 we don't really need. 8 times 7 times 5 is 280. There we go. And so voila, we have it. All right, and then for C, same thing. The biggest on the numerator is 11. The biggest on the denominator is 7, so we'll be able to cancel out a 7. So 11 times 10 times 9 times 8 times 7 factorial over 7 factorial, 4 factorial, which is 4 times 3 times 2 times 1. So we cancel out those 7s. Also 4 times 2 is the same as 8, so we'll cancel out the 4, the 2, and the 8. So we're just left with 3 and 1. So 3 on the bottom, and then on the top, 11 times 10 times 9, which is 990. And then we can divide that by 3 and get the answer is 330. Whenever we're dividing factorials by factorials, there's usually a shorthand way to do it. We can easily just cancel a bunch of things out, which is really good, right? We want to make sure that we take the path of least resistance, right? Because reality is mathematicians, they're very lazy, right? Why would we do extra work that we do not have to do? It does not make sense to do this. Good. All right. Well, that is it for factorials. So that's really good. What I'm also going to talk about in today's lesson as well is permutations, because they're very much related to factorials. We're going to need factorials. We're going to need to use what we learned in order to do permutations. So let's do permutations today too. So what is a permutation? A permutation is an arrangement of n distinct items, and all the items are arranged in a particular order. So long story short, something really key about permutations that I'm going to drill into your head for this whole semester is that order matters when it comes to permutations. Order matters, okay? So, for example, let's say that I would like to know how many different ways 5 students can sit on a bench. Well, order clearly matters, right? It matters who's sitting first, who's sitting second, third, fourth, and fifth. Or if I want to know how many different ways can 5 people or 10 people or however many people line up at the bus stop, same thing, right? It matters if you're first, you're second, you're third, and so on. You know, what other times might it matter? Well, let's say people are running a race. Well, you probably care whether you got first, second, third, fourth, fifth, sixth, or so on, right? You probably care which order you were placed in this race, right? And so whenever there's a certain number of objects or items, or it can be people as well. I know it says items here, but it can also be people. It's how many arrangements of them could we possibly have, okay? So if n items are arranged in the order for n possibilities, then there's n factorial ways of doing so, okay? And then I also want to just briefly mention this notation for permutations as well, where n factorial is the same as npn, right? We'll talk about what np something else is later, but these are the same thing in this case. We would just say n factorial here. Now, I want to talk about why is this true? Why? Because this kind of tells us that if we have n items and we want to know how many possible positions there are, the answer is n factorial. But why? Why is that the case? So I'm going to do a very simple example here where I want to know how many ways we can rearrange the letters A, B, C, D, for example. I would like to know how many ways could I arrange these letters. It doesn't have to make a real word, because I don't think we can really make a lot of real words, or I don't even know if we can make any real words with A, B, C, D. I'm not a Scrabble person, but how many ways could we rearrange these different letters? Well, let's think about it. So some letter needs to go here in the first place, place one. Some letter needs to go here in place two. Some letter needs to go here in place three, and some letter needs to go here in place four. So how many different letters are possible, could possibly go into the first category? Well, any of them, really. It could be A, it could be B, it could be C, or it could be D. So there's 4 possibilities here for how many. Okay, now that we put something in the first spot, then how many can go in the second spot? Well, let's think about that. Well, we already put some letter in the first spot. We don't know which one it is, but let's say we put A in the first spot. That means only B, C, D are left, so that's only 3. And same thing if it's another letter. Let's say we put B in the first spot, then we only have A, C, D left. Let's say we put C in the first spot, then we only have A, B, D left, so that's still 3 things. And let's say we put D in the first spot, well, then we only have A, B, C left, so it's still 3 things. So regardless of what letter is put in the first spot, either way, we still have 3 distinct possibilities for what could go in the second spot. Now that we filled the first and the second spot with one of these letters for each spot, that means there's only 2 letters left. Now we don't know which 2 are left, but we know that 2 of these letters are gone in the first and second spot, and we have 2 of the 4 letters left. Then how many possibilities do we have for the very last spot? Well, only 1, because all 3 of the other letters have already been placed, so there's only 1 possibility for what could go in the last spot, and that's just whatever letter is left, right? If we already used A, B, and C, that means D goes in the last spot, or if we already used B, C, and D, that means A goes in the last spot, and so on and so forth, right? And so this, this looks strangely similar to me to something we just saw. 4 times 3 times 2 times 1, well, that's the same as 4 factorial from what we learned earlier today. So it's 4 factorial. And we can apply this same logic to any of these problems. If I want to know how many ways 10 people could line up at the bus stop, well, how many different ways could the first person line up? Well, or how many different possibilities are there for the first person lining up there? Well, just 10, right? 10. Now that someone chose to line up there, how many people are left who could possibly go in the second spot? Well, 9, and then 8, and then 7, and 6, and 5, and 4, and 3, and 2, and then 1, right? And so we can use the same logic and apply that same logic to other situations as well, right? Here we had 4 letters, so the answer was 4 factorial. And so that's why. I think a lot of times students, they'll know that the answer is n factorial, but won't understand why that is. So I wanted to make it very clear that this is why, right? This is where that n factorial comes from. It's not just random. It's there's a lot of thought put into why that is. Okay, so let's go to example 1 next. Example 1 says there are 5 students who are lining up for their chance to throw a baseball at a dunk machine to drop their teacher. In how many ways could the students line up? Well, let's see. There's 5 students. I'm guessing they all want the first spot. They probably all want the first chance to throw that baseball and junk the teacher. But, there's 5 different possibilities there for that first student, right? And then how many, if anyone who didn't get the first spot probably is rooting for the second spot. So there's 4 of them left. Now the first 2 spots are taken. There's only 3 students left to go in spot 3, and then only 2 students, and then only 1 student, right? So again, this also confirms, even more to us that it's 5 factorial is the answer. So there's actually 120 ways that the students could possibly line up, right? There's so many different permutations of that. So therefore, the students can line up. The students can line up in 120 different ways. And that seems like a lot, but I confirm that is the correct answer. Good. All right, let's try a second example. It says, if there are 7 colored sheets, red, white, blue, green, black, purple, and pink, how many ways can those flags be arranged if the white flag must be in the middle? Okay, so this is a good question. This is a good question. So some of you might already know the answer, and if you do, fantastic. But I'm going to go through this slowly in case you're not really sure how we would do it here. So I'm going to, write down 7 spaces. 1, 2, 3, 4, 5, 6, 7. But there's a condition here. The condition is the white flag must be in the middle. So we know that this one is definitely the white flag. Okay? So now how many flags are left? We don't have the white flag anymore. We already used it. We just have red, blue, green, black, purple, and pink. So how many possibilities are there for the first colored sheet? Well, there are 6, right? Because it can't be white because white's already in the middle. But it could be red, blue, green, black, purple, or pink. So that's 6 possibilities. How many possibilities are there for the second one? Well, we can't use white, and we also can't use whatever colored sheet was already chosen for the first space, so there's only 5 left. How about for the third one? Well, there's only going to be 4 possibilities here because we can't use white, and we also can't use whatever the first and the second ones were chosen. For the fourth one, there's actually only one option because we know for sure it's white, and so there's only one thing that can go there, which is white, because in the question it told us how many ways can the flags be arranged if the white is in the middle. So there's only one possibility for middle, which is that it's white, if we are to follow the instructions here, which we are. And then how many can go for this next one here, the third to last? Well, it can't be white, and it also can't be any of the things in spot 1, 2, and 3, so therefore it must be 3. Then there's only 2 left for the second last space, and then only 1 left for the very last space. So this is 6 factorial, right? If we look at this closer, this is 6 factorial is equal to this, because the times 1 right here that's in the middle, that doesn't actually do anything. This is just 6 factorial, and that's all. Now, what is 6 factorial? What is 6 times 5 times 4 times 3 times 2 times 1? It is going to be 720. So therefore, there are 720 ways. So this is really just the same as how many ways could we line that up if there were 6 colored sheets, right? Because we already placed, since we know the white one has to be in the middle, there's no mystery there, right? There's only really 6 that we're rearranging and mixing around. We're not mixing around the white one. In every scenario in this case, the white one is in the middle. Now, if they didn't tell us the white one was in the middle, then it would be 7 factorial, because that would mean that we're actually moving around all sheets, not just, 6 of them. Very good. Okay, let's move on. Number 3 says, in how many ways can a basketball team of 15 take a picture if the captain must have their 2 assistant captains beside them during the picture? Okay, so this one is a little bit more challenging because it doesn't actually tell us that the assistant and the captains must be in places 1, 2, 3 or something, right? They didn't tell us where they are. They just said they must be together. So what we're going to do for this one is we're going to think about, this group as one person, right? Even though I understand that the captain and the 2 assistants are actually 3 people, but we're going to pretend that they're one person. Now, why is that? Because they must move in a group together, right? The captain must be in the middle, and the 2 assistants must be beside them. Yeah, the captain must have their 2 assistants beside them. So that means we have captain, and then we have assistant on one side, assistant on the other side. So this group, it moves together, right? And so let's think about that. If the captain, and then we have the assistant, and then we have the assistant over there like that, we're going to consider that to be one person. So in that case, we're going to pretend there's only 13 people, so it would be 13 factorial. All right? So that's important, 13 factorial. Why is that? Well, because if the captain goes, the assistants go with the captain, or if the assistant goes, then the captain and the other assistant must go with them. Now, there is one other thing I want to keep in mind with this, which is that we must multiply by 2 factorial as well. Now, why is that? That's because the assistants could switch places. The assistants are not just 2 identical people. The assistants are unique people. So if we have assistant 1, then the captain, then assistant 2, that is a different permutation from if we had assistant 2 first and then the captain and then assistant 1. So we must multiply by 2 or 2 factorial, right? I guess 2 factorial is 2, but in general, it's good to have the factorial sign. If there were 3 people who could be swapping around, then it would be 3 factorial, right? 3 factorial ways, not just 3 ways to swap 3 people around. But in this case, they specified the captain must be in the middle, so he can't move in any of these cases. It must just be the assistant swapping places. And so that's why the answer is 13 factorial times 2 factorial there. Very good. Now, we could do this out if we wanted. However, whenever we have factorials that are this large, it doesn't really matter if you evaluate them or not in a lot of cases. I mean, do it whichever way is the way that your school does. However, in a lot of settings, you would not have to simplify this further. You could just say 13 factorial times 2 factorial and just leave that as the answer. I will evaluate this, though. I think some people might like to know, try to conceptualize what this is. However, it wouldn't necessarily be a bad thing to just leave it there because it's going to be a very large number. The number is 12454041600. So a very, very large number there. Let's see, just how large is that? Yeah, let's see, that's 12,454,041,600. So that's a really, really large number. So you can see what I meant by, it's probably not really that important to evaluate it, because I think to most of us that seems like just such an outlandishly large number that we wouldn't really care to have much to do with, perhaps. But that's how many ways, over 12 billion ways that this team could take their photo, even with the condition that the captain and the assistants must be together, not only together, but the captain must be in the middle and the assistants must be on either side. So just kind of, it's important to kind of have some thinking here as to, well, how would we do it in this specific scenario when we have this restriction on where the captain and the assistants can be sitting? Very good. All right, so there's actually even more on permutations. We're actually going to talk even more about permutations in this next one. That will be a lesson for next day, though, so I will see everybody next day for that. Bye, everyone.